Hi friends, let's continue our analysis of problem 2909 and 2908, minimum sum of mountain triplets. So in a previous video, we explained a simulation solution based on mean heap, and we analyzed the time complexity. So based on the analysis there, so here in this video, we are going to give a solution based on pure linear scan. So in the solution here, we will have a time complexity O of n, in other words, linear time complexity. So let's briefly recall the problem statement. Here we have an array of integers. So a triplet is called a mountain if the middle one corresponds to a largest element and the two sides are smaller. So we don't impose relations of the two sides with themselves. Right, so in other words, so nums I can be and the nums k can be any relation as long as they are both smaller than the middle one. So let's call this G the peak, right? So here we want to return the minimum possible sum of a mountain triplet of nums. If no such triplet exists, we're going to return -1. So in our previous video, we already know that. So in order to do this problem, for each index, if we want to use this I as a mountain peak, so in order to find the minimum possible mountain triplet sum, so we need to find the left smallest number to the index I and the right smallest number to the index I, and we want to check if the smallest number to the right and to the left are both smaller than this number corresponding to index I. If so, we have a valid mountain, and in that case we are going to compute the sum, and then when we do the linear scan, we can actually get the minimum possible sum. So the case thing is that for each index we are going to get the smallest number before that index. So this actually can be done using something mimicking the prefix sum or suffix sum, but the function here is not a summation rather, but the minimum, right? So let's look at the solution. So first, I'm going to use the same notation as the previous video. So we have this. So we are going to initialize as float infinity times n. So here n is nothing but the length of this nums list, right? So here, if you think of the zeroth element in this left smallest, because for example here 8 to the left there's no element, so we are going to set the smallest number to be positive infinity. The reason we set it as positive infinity is to adapt the problem return, because we want to return something minimum, right? So that's the one thing. So now let's iterate, right? That's for I in range. So we can start from index 1 up to index m. So what we want to set for left smallest I is the smallest number before this index. So we want to find this one. So left smallest, the previous state up to index I, right? And then we want to compare with the current number, nums I minus 1. Notice that here it's still I minus 1. So if you see, if we use this as a, if we add something, for example, left smallest I minus 1 plus this number, this is nothing but prefix sum, but before index I, right? But here the function we are using is mean. Essentially the same thought. So this line of code will set this left smallest. So now let's set the right smallest. I'm going to copy this block and put here and make some changes. I'm going to change left to be right, and then here right, and here right, and also I need to change the index. So we need to start from n minus 2. So ending before -1, the step is -1. So here right smallest, I'm going to look at the right. So here will be I plus 1. Again, here is not I, it's I plus 1, because we want to compute the smallest element to the right of I, strictly to the right. So this way we finished the setting for left smallest and the right smallest. Then we just need to do the return. So again, we use the exactly same code for as the previous video. We get positive infinity, and then we check the possible mountains. So for A, B, and Y in zip. So A, let's use smallest left, or left smallest, and right smallest corresponding to B, right? And let's use this one nums, right? So now let's check mountain relation. So we want A strictly less than Y and B strictly less than Y. As we mentioned, we do not impose any relation between A and B. So if this is the case, basically it means Y is a peak and corresponding to the two sides AB. So then we are going to take min operation again. So pre-state and A plus B plus Y, right? And then we just need to do return, do proper return. So we want to check if there is a mountain at least. So we want to check if result is less than float infinity. So if this condition holds, basically means there exists a mountain triplet. Otherwise not, we are going to return -1. So if this forms a solution format, if you look at this code, actually it's very short and very simple. So basically we compute these two pieces of information and then we do a linear scan. So here it's something like dynamic programming, or like we do prefix sum or suffix sum, right? So this for loop is O of n, and this for loop is O of n, and here is also O of n. So total time complexity will be O of n. So now let's first do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes the generic case. So I guess for now, if you look at the two videos together, so we actually take such a route. First, when we look at the problem, we give a simulation. There, in the first video, we used min heap. And then we use min heap to compute this part of information and this part of information. And we found that there are some redundancy in the code. So we write another hyper function so that we can call the function twice to get these two pieces of information. And then that we finish the first video. In the current video, we do the same thing, but we didn't use heap, right? So we just use some idea like prefix sum or suffix sum or dynamic programming. After we get these two pieces of information, then we just do a linear scan to check mountains and return the proper result. So I guess if you putting the two videos together, we can see the root. So we actually from a slightly complex solution to arrive at a simpler solution. So if you like, you can write a simple a hyper function to, like in first video, to get so that we can call twice to get these two pieces of information and then do this. In other words, you can make it more modularized. So with that said, I will not further optimize the solution formats. So I hope that the two videos together will expose you some useful information. Thank you.